화면 보이시나요? 네, 감사합니다. 아직 많이 들어오지 않으셔서 한 5분 정도 있다가 바로 시작하도록 하겠습니다. Okay, let's get started. Hi everyone. I'm today's TA Hyunkyung, and today is the last practice session of this lecture. We'll cover three topics here today. The first one is implement and training the OpenAI's clean model, and we use a pre-trained clip for the zero-shot classification task. And lastly, we will cover stable diffusion training with classifier-free guidance. And first, we download and import some necessary sources for the practice session. And the dataset we will use for the clip training is the Flickr dataset. And the Flickr AK dataset literally consists of 8,000 image text pair, where each data point consists of a single image and five captions describing that image. And here is an example. The five captions below describe the girl in the image. And the following codes include the pre-processing step for the dataset and split it into training, valid, and test set. Then now let's implement the CLIP model. And this image illustrates how CLIP is working. And this session, we will explore how the model is trained using the image and text embedding generated from the both image and the text encoder. And the text encoder here works by converting the written text into the text embedding, and which allow the model to understand the text and connect it to images. So this is the code I for the text encoder, and I give you the text encoder class like this. We use the transformer encoder for the text encoder architecture. And in this class, the fourth function is currently empty. So I give you 5 minutes to implement it. After 5 minutes, we will leave it together. And the fourth function takes the tokenized caption as input, and the desired output for this function is the global text embedding that represents the entire text. Okay, then let's leave it together now. Uh, Here is the code. In the first line, we first convert the input text into embedding vectors. This self-embedding function map each token in the text into a fixed size vector. The resulting shape of X is batch size by sequence length by transformers width, where batch size is the number of text sequences being processed at once, and the sequence length is the length of each sequence that meets the number of tokens, and transformer width is the size of the embedding vector for each token. And the transformer does not know the order of tokens in the sequence. So to give the model about this information, we add positional embedding to the text to the token embedding. And this function select the position embedding corresponding to the sequence length. And adding this information ensure that the model understands the position of each token within the sequence. And here we rearrange the dimension of the tensor, and the transformer expects the input shape to be sequence length by batch size by transformer width. This reordering ensures that the transformer processes the data correctly. Now, the embedding are passed through the transformer layer. The transformer applies self-attention and other layers to capture the relationship between tokens in the sequence. The output shape remains the same with input, and after processing, we revert the tensor back to its original shape, batch size by sequence length by transformer width. And then here we locate the end of text token in each sequence. In many text processing tasks, sequences are padded with the special token. Usually it is a zero to make them the same length. So the actual end of text is marked by an end of text token. And this code identifies the index of the EOT token in each sequence. After that, it then extracts the embedding corresponding to the EOT token for each sequence to capture the representation of the entire text. Finally, the embedding is projected to the predefined dimension space using a linear layer, and this is often done to make the embedding more compact and suitable for downstream tasks. Okay, then let's move on to the next code. And now let's implement the image encoder. I also give you the 5 minutes to write the code for the following empty section here. Uh, we also use transformer encoder for the image encoder architecture. And just like the text encoder, the desired output for this function is the global image embedding that represents the entire image. Okay, let's leave it together. And here's the code for the forward section. And first, the input image X is passed through a convolutional layer, and this operation extracts feature from the image and reduces its spatial dimension, and resulting in a tensor with dimension batch size by width by grid. And the next two steps are for reshaping and transposing. The spatial dimension, here the grid by grid, are flattened into a single dimension representing image patch, resulting in a tensor with shape batch size by width by num patch. And the dimensions are transposed to arrange the data as batch size by num patch by width, where each element in the sequence represents a patch of the image. Actually, these three lines prepare the input data for processing by the transformer. The input image is first processed by a convolutional layer to extract feature, and then it is transformed into a sequence of patch, which is the pseudo format for the transformer's input. And the transpose operation ensures that the dimension of the tensor are in the order expected by the transformer. After that, a learner request embedding is expanded to match the batch size and added to the sequence. This embedding provides the global representation of the image. And the class embedding is concatenated with the patch embedding, resulting in a sequence of non-patch plus one element. This adds a special token to the beginning of the sequence, representing the entire image. After that, the positional embedding are added to provide information about the spatial relationship between paths in the image. And this resulting sequence is passed through a transform encoder to capture complex relationship between image paths. And before that, the permute operation rearranged the tensor dimension to fit the transformer's expected input format. And after processing, the dimension are permuted back to restore the original order. And lastly, the output corresponding to the class embedding, and here the first token in the sequence is extracted and passed through a fully connected layer, and this provides a single vector that represents the entire image. And this part here is the heart of how CLIP learns to connect images to text. A contrastive loss in CLIP helped the model to learn by comparing pairs of image and text. And it rewards the model when it correctly matches an image with its corresponding text and penalizes the model for incorrect match. And this approach effectively aligns the representation of image and text in a shared embedding space. And uh, I will give 5 minutes to implement the contrastive loss section, and this function takes both image feature and text feature, and those are extracted by the image and text encoders. Okay, let's review the code together. Here's the code. These first two lines normalize the image feature and text feature, and the normalization ensures that the feature have a similar scale. And then this perform a matrix multiplication between the image feature and text feature, and this essentially calculates the similarity between each image and its text description. And the resulting matrix represents the model's prediction of how well its image matches its text description. And this line creates a tensor containing the correct label, since we assume that the image and text at the same index in the batch are matched, so the label are simply a sequence of numbers from 0 to the batch size. And next part are how we calculating the loss. This function calculates the cross entropy loss and it measures the difference between the model's prediction and the true label. And this is the loss calculated for the image to text direction, and it measures how well the model predicts the correct text description for an image. And the below line is very similar to the previous one, but it calculates the loss for the text to image direction, and it measures how well the model predicts the correct image given a text description. And finally, the function returns the average of the text to image and image to text losses. And this code block defines the main structure of the clean model. And this part defines the main structure. This part set up the configuration for the clean model and then create an instance of the model using those parameters. And here's the code for training the model. And I think you guys are very familiar with the model training as there are a lot of practice session before. So we just skip this part and move on to the next section. Yeah. The next section is zero-shot prediction. The important thing of CLIP is this model can do the zero-shot prediction task. So we will cover zero-shot image classification using the CIPA 100 dataset in this section. So first, we have to download the dataset and the pre-trained model. And while downloading, I will briefly explain what the zero-shot prediction task is. And let's just imagine you have a picture and want to know what's in it. And instead of training a model to recognize a specific object, you give Clip the picture and a set of text description like a photo of a dog, a cat, or a car. And then the Clip compare the picture of description and pick up the one that's best match, even if it has never seen that specific object before. And the training technique plays a crucial role in this ability. And for sure, alongside learning from a massive amount of image text pair from dataset from the internet. Anyway, that is contrastive learning. As this encourages the model to learn similar embedding for image and their corresponding caption while pushing apart embeddings for unrelated image text pair. And this results in a shared embedding space where image and text that are semantically similar are located close to each other. And during zero-shot classification, click compare the embedding of an input image to the embedding of a set of text that represent different objects. The object with the highest cosine similarity to the image embedding is predicted as the images class. Okay, then these two parts demonstrate how the clean model process both image and text. The model expects image in a specific format here, and this pre-process function ensures that the image is compatible with the clean model. And the tokenized function will convert the hello world, for example, string into a sequence of numerical tokens to the clean model that can understand. And this token represents the input text in a way that the model can process. We're going to feed 8 examples of image and text description to the model and compare the similarity between the corresponding feature. And this line create a dictionary called description. The keys are file name of images from the library, and the value are the text description that describe each image. And the remaining part here are code for set up the image for the model input. First, we open the image and add the original image to the list and apply the clips predefined preprocess function to convert the image to the proper format for the model input. And we're going to build features. This code is for preparing the image and text data and then extracting feature then from using the clean model. And these below three lines are essential for comparing image and text feature in the clean model. And we calculate the cosine similarity to measure the relationship between image and text and their text description. And here's the code for the visualization. Let's see the result. Uh, yeah, this code produces a visual representation of how well the clean model understands the relationship between the text description and image. And we can see that which description are most similar to the which image based on the color and the numerical value in the heat map. As we can see in this figure, the clean model demonstrates the ability to effectively associate their text description with corresponding images in a zero-sum manner. And looking closely at this ledger, in the first row, we can see that the similarity score between the caption "a cup of coffee on a saucer" and other images show that the original image aligned with this caption achieved the highest similarity score. And also in the first column here, yeah, examine the similarity score between this cup of coffee image and other caption show that the original caption aligned with this image also obtained the highest similarity score here. Okay, then let's do the zero-shot classification together. This part of the code perform the zero-shot image classification task using the pre-trained clip and the CIPR100 dataset. And this line creates a list of text description of each of the 100 classes in the CIPA dataset. And each description is permitted as this is a photo of a label, and a label here is replaced with the actual class name such as airplane, automobile, or bird. After that, we first tokenize the text description into a sequence of token. And we use the clip text encoder to convert this sequence into text embedding. After normalization, we then compare the image picture with the text picture to find how similar they are. And lastly, this similarity score to predict the top 5 most likely class for each image. Look at this example. We can see that the clean model predict the clean model predict the label man with the highest probability score for this image, and the image below it predict the label motorcycle with the highest probability for the motorcycle image, and also this image show that this leader show that the model predict the label woman with the highest probability score for this real woman image. And this ledger shows that the clean model can perform zero-shot classification task. In other words, it can effectively match images with the most relevant labels without requiring additional specific training. And this concludes the section about clip, and now we will move on to stable diffusion with classifier-free guidance. Okay, here we train a class condition diffusion model on MNIST. And first, we download and import the necessary libraries. Then we prepare the MNIST dataset for training. As shown in the image below, this dataset consists of 28 by 20 grayscale images, and each image represents a number, the handwritten digit. And for this section, we will use BERT, this uncased, very shallow BERT model for the text encoder. And here, this code creates a standard unit 2D model with some additional input channel. And this extra channel are reserved for the class condition information. And this function here map the class label to a learned vector of shape class embed size here. And we already define 128 here and through an embedding layer. And the embedding layer is like a lookup table that convert the integer label. Here we will use the digit label into a dense vector representation of size class embedded size. And this learned vector we just call this as a class embedding. And this class embedding captures the essential feature or characteristic of the digit class. And as I already mentioned earlier, we use the BERT model for text encoder and also use the BERT tokenizer for tokenizing the description. And here, I will give you 5 minutes to write code that convert this label into text description and encode them using a BERT model. And when writing a code, it is important to consider that the classifier-free guidance will apply to improve the model's generation quality. So as a result, empty string may appear as label. So therefore, the code should account for cases where the label is either an empty or not. Okay, then leave the code together. Uh, sorry. And this function take a list of label that represent the desired digit to generate and process them. First, this code transform the input into text description. If the label is not an empty string, it format the label as a photo of the digit label and indicating a class-specific condition like a photo of the digit 3 or digit 8. And if the label is an empty string, it leaves the result as an empty string like this. And this represents the unconditional training case and where no class label is provided during training and generation. And it allowed the model to learn to generate sample without relying on specific class information. And then this code tokenized this texture description using a BERT tokenizer. Uh, After that, next, we feed these tokens to a BERT text encoder. And then finally, it takes the output of the BERT encoder, and this will be used as a class condition information later in the forward pass. And here in the forward pass, the first line, this function we define earlier, this line extract embedding of the label, and this code extract the embedding of the CRS token from the class tensor, and it provides the global class representation from BERT's output, and this embedding is used for conditioning the image generation. We passed the output tensor to linear layer, and then reshape using view function for concatenation with the input image X. And this line concatenate this information as an extra channel from unit input. And, and then finally, we feed the output that input into the unit to get the final prediction, and the unit process this input using both the image information and the class conditioning to guide the generation process. And for training a diffusion model with classifier-free guidance, we first create a scheduler. Here we use DDPM scheduler and set the training time step as 1,000. And here is the code for training. Mm, I get the other parts are very similar as the diffusion model we practiced earlier, so I will explain the other parts very briefly. And the first line is scale their pixel value to the range of -1 to 1, which is often beneficial for model training. And these three lines are generate random noise and select random time step and add the noise to the input image using the noise scheduler, and this create noise version of the image. And these two lines are for the implement the classifier-free guidance technique during training. And this could randomly decide whether to provide the class label Y as a condition or an empty string as an unconditional training. If the random value is greater than 0.1, the class label is used as a condition and converted to a string, like a photo of the digit 3 we defined earlier. And if the random value is less than or equal to 0.1, the condition is set to an empty string, meaning that no class label is provided. And this represents unconditional training. And this helps the model to learn to generate both conditional and unconditional samples. And once the training is finished, we can sample some images fitting in different level as our conditioning. And this formula show a classifier-free guidance during inference, and given a conditional diffusion model where C is the condition input, and here we set the C as the class label, that means a digit, and an unconditional model. The classifier-free guidance combines these two models by adjusting the strength of conditioning during sampling. And W here is a hyperparameter to control the strength of the guidance. And typically we use this W as greater than 1. And this formula ensures that the model generation is influenced more strongly by the class level and to improve the quality of the generated sample while also maintaining the diversity from the unconditional model. And here's the code for sampling using classifier-free guidance during inference. And I also give you the 5 minutes to write the code for this line. Okay, the time is over. Have anyone implement this? If so, could you show me the code in the chat window on how you implement about this code? Actually, I'm currently training the model for classifier-free guidance ledger comparison, so which is takes some time. In the meantime, I will give you more time. So for those who haven't implemented it yet, please give it a try. Okay, I guess the model training will be end soon, so let's just review the code for sampling. Here is the code I implement for classifier-free guidance during inference. Let's see the code step by step. The first line is this is the hyperparameter that control the strength of classifier-free guidance. And this is the code for the input noise, and X is initialized as random noise with this shape. And Y contains the class label for the images, and each class label is repeated 8 times to match the number of images and resulting in a label for 80 images. And this code line shows that the model make a prediction by condition on the labels Y here. And about this line, the model make an unconditional prediction using an empty string, where the empty string are passed instead of label. And here's the code. The final prediction is obtained by applying the classifier-free guidance, and the difference between the conditional and unconditional prediction is scaled by guidance scale and added to the unconditional prediction. And this step enhances the influence of the class label on the generated output. And finally, we can see the generated image below here. Looking at the images, we can observe that the various samples are generated corresponding to each class label. When we looking at the at this code for guidance for classifier-free guidance, this code block is quite different with the original formula. When we follow the original formula for the guidance, it will be guidance scale 5 condition scale 5 conditional here. When we follow the original formula here, the code will be like this, but but the both formula achieve the similar result, and the modified formula is often used in practice for its simplistic and ease of understanding. And actually, in many implementations, the modified version is preferred because two reasons. The first one is simplistic, as the modified formula involve a direct addition of the weighted difference between the condition and unconditional image, which is computationally more simpler. And this version make it clearer how the model adjusts the condition image based on the unconditional one. And the idea is that the unconditional image provides some base image, and the difference here between the conditional and unconditional image is added to it. Actually, the choice of formula is typically a matter of preference or convenience in implementation, so as both are equivalent in the context of guiding the difference process. And I guess the training for the model is done. So additionally, let's examine the result generated without applying the classifier-free guidance. Mm, For this, just simply erase the unconditional prediction and only contain the conditional prediction as a guided noise. Mm, Quite some time for sampling. Okay, let's see the ledger together. Of course, the current ledgers here are generated from a model trained only 5 epochs, so they are not an ideal. However, by comparing the two ledgers, we can qualitatively observe that the images generated with classifier-free guidance have higher quality and diversity. Okay, let's wrap up today's session. If you guys have question, you can just you can just send on text here, or if you don't have any questions so far, you can just leave now. Thank you for your effort, and we will end up here for today.